today. Well, we do have a very important topic to discuss. I can understand that. Hello, my name is Viva. I'm from Agile Accelerator, and I'm going to motivate this time today for you guys. I'm very, very happy that it's such a success that so many of you came today, and that our wonderful startup Gridhound gave us the opportunity to jointly coordinate this event and to organize it. Thank you for that. First of all, a little bit about Agile, who we are, what we do. So Agile is a corporate accelerator and incubator at E.ON. We have been working since 2013. We started actually as an internal program, and our main goal was to support innovation within the company. However, only 1 year later, we realized that actually innovation does not only come from inside of the company, but also from the outside. So we decided to combine the powers of the internal E.ON employees as well as external startups and bring innovation and new solutions to E.ON customers. Are we successful? I would say so. As you're going to see a very good example today on the stage. And let me just say a few reasons for that. So first of all, it's a lot of learning from ourselves, from our startups, a lot of working together, a lot of good ideas coming from inside of the company and from outside of the company, and of course, a very, very important part is supporting the board. And every time when we talk at different kind of events and when we talk about different accelerators existing, they're all saying they have the same problem. They have a lot of people within the company supporting them, but sometimes this support and this holding hand does not come from also the high up. And on that note, I'm very happy to invite and to have here today Dr. Wildberger. Thank you for coming, and the stage is yours. So he's going to start the event of grid awareness with his keynote speech.
Thank you very much. Do I need a microphone? Can you hear me or not? The microphone, is that better? Okay, I'll try with microphone. First of all, thanks very much for being here. It's great to be here. Before I start talking about E.ON and what we do with digitization, a bit of innovation, I'd like to say that we are very proud of working with so many startups, with universities like ALTEA Aachen, great collaborations that mean a lot for us and also for our future. And as you know, we've announced the takeover of Energy, our main competitor, and that's going to be probably done Q3 2019, pending now all the regulatory approvals, etc. All of those, this takes time. But one thing is very clear, also for the new E.ON, innovation will be a crucial part. And the make or break for energy companies in the future is also how much we can renew our business models, how much we can also establish new businesses, and that requires innovation, collaboration, working with research institutes, with startups, and bringing that into our business. There's also very much a cultural change. So what I'd like to talk about very briefly, about a few things that we are doing at E.ON, and then I will hand over to the next speaker, and then we have a pen. So the first thing I like to say about digitization, because I always find this view pretty impressive, how long it took to penetrate technology till you reach actually 50 million people, if you take one KPI. So how long did it take till 50 million people on the planet used the radio when it was invented? It took 38 years. Television, 13 years. Internet, 4 years. iPod, 3 years. Facebook, 2 years. And Pokemon Go, only 15 days. I'm not sure we're still playing here in this room. Have we found any number? Okay. But what this means is the speed of innovation and penetration of technology adoption, the cycle time has become so small that we see technology evolve so much faster. Just assume the iPhone was launched 2007, and just that innovation in combination with other things has changed everything. That's 10 years, but we'll see more of that going forward, not just Pokemon Go. There are some forces behind digitization, why it impacts every single industry, and why it is so profound. In maths, you would say it's an axiom, or something that is of so fundamental, first principle nature, that it just changes the fabric also of how we do business. And there are some fundamental dimensions behind why every industry is impacted by that. First is that digitization allows an incredible richness and incredible reach, basically the maximum of both. And that means you can offer millions, billions of products at the same time, organize that, but you can also reach any part of the planet once you're connected. We don't have that with classic retail, with bricks and mortar retail, but we have that, for instance, of course, online. The second one is a fundamental principle that in many industries we see the notion of zero marginal cost. So you see that in photography. Once it costs $1 to produce the next print, the next unit of digital photography, the marginal cost is zero. That changes very much the business model. And the same thing happens to us, that the incremental kilowatt hour produced by clean, renewable energy doesn't cost anything. So which kind of business models emerge from that? And then of course you have the power of data. First the availability of data, but then you have connectivity, you have computing power, you have sensors, all those things coming together. So you have the ability to master with algorithms enormous amount of data and create insights that the human brain can't master. So if you look at algorithms, what algorithms today can process, the human mind actually can't do, especially in specialized tasks. Like what the hype is about AI, which is still quite narrow, but it's very fundamental. We also see, as on the first chart, an acceleration of innovation. There are some theories around, which is like Moore's law in semiconductors. We said every 2 years, 1.5 years, you have a doubling of speed. Every 7 years, you have a double speed of the rate of innovation at the moment. So that doesn't mean we just change, but also the speed of change, the velocity is changing, accelerating, which is great, but also a challenge. And what then finally is that you have a lot of business models that grow exponentially. They're not just linear models, but because of richness, reach, zero marginal cost, all of that, you have so many business models where you see more and more at this point in time the winner takes it all. Especially if you look at the largest market cap of the largest companies in the US or in China, the top 3 companies are worth 3 times more than the whole DAX in Germany. So you see more and more of the trend of the winner takes it all, which is also fundamentally down to the nature of those trends. But that impacts every single industry. And last but not least, customers have more power because every one of us is more informed, we think, if we choose the right information. But we have access to all sort of data at the fingertip. And hence we actually also have more choice. And we feel that in the way we behave, so customers have more power. And so the energy world is changing. Now we'll run through very quickly, you know, probably all of that anyway. But the old system in the 19th, 20th century that was built is very fossil fuel-based, nuclear power-based, so large power plants with transmission lines to connection points. So it's a very rigid system, a very centralized system, where you actually don't worry very much about energy anymore in the old days, apart from the invoice. But the problem was largely solved. It was a supply relationship, monopolistic structures. And that is falling apart. It doesn't happen overnight because it's a fixed asset industry. It takes time to change such a system, but the change is more fundamental than we still believe as an industry. So sometimes a 10%, 15% shock to a system can create totally different economics. And that's exactly what happened in our industry. Hence we spun off our generation business, and all of that changes that RWTH has done is a consequence of that. So the world is becoming green, cleaner, it's becoming much smaller scale, decentral. It also means that customers more and more have the power, if they choose so, to produce their own energy. They become part of the system, it becomes more and more connected, and it's customer-centric. And in that world, the distribution grids play a fundamental role. They will create more and more connections. We will see the emergence of smaller networks, hubs, interlinks that become also the topology of the network is changing. And that again doesn't happen overnight, but it also requires data, it requires software, it requires real-time management. So, and that's what we do already today at E.ON. Large parts of our investments is not just going into copper, it's going into software. So if you look at our distribution companies today, there are lots of initiatives underway how to use the power of data. Otherwise the lights would go off, by the way, because you can't manage the grid otherwise. And we're also having a lot of innovation projects to build platforms behind the grid that enable that decentral energy world where customers can exchange energy. We have microgrids where you can go off-grid, where we have bidirectional flows, multidirectional flows. There's enormous innovation happening in Aachen about combining electrons with data packages, which I find fascinating, and I'm happy to see that work progress. So this is actually what happens, becomes much smarter, much more local, and that's what E.ON also stands for. The core of our business going forward will be also grids. 80% of our business will be networks based. And around the network, we will also build customer solutions, so the endpoints, if you like, to customers. We try to engage with customers with increasingly more solutions, from storages to electric charging, to solar, smart tariffs, etc. So the world becomes more decentral and also more engaging. It becomes bidirectional or multidirectional because you also interact with the grid with others. You create communities, if you like. Two examples, or before I say, for us, that gets often, when you compare, what about Google? What about all these fantastic, fancy digital plays? We are not a digital pure play, and I don't think we'll ever be. But the art is to combine an asset world with a digital world, so you create a good mixture. And that's not easy, but it's also not easy for a digital pure play to learn how to use assets. So we are very proud of being able to run assets, but we have to combine them with the digital world. Two examples only what we're doing. This is what we call predictive maintenance. So in the past, you would have tables based on experience, where you would go and just change network elements based on age, based on what people think, what the supplier tells you, the transformer, etc. And we are switching that more and more now to automated algorithm-based decision making. So we have deployed sensors across the network, and we increasingly do so. So we collect all the data, we combine it with weather data. And what you see here in an old or traditional world based on experience, you would see a linear curve, meaning in order to increase 50% stability of your network, you replace kind of 50% of your network elements. And that relationship based on those data insights is changed, and we see a lift of 1 to 5 at the moment, where the algorithms stand. They become better. They also use weather data, data from the environment, also network load data, planning data. So all those things that are multi-correlated are factored into those algorithms. So that's something we're deploying, and we are building also in-house largely. The second one is, of course, if you look, those pictures is the sources of renewables, wind, solar in Germany. So each dot would be a major power generator on a distributed basis. So we've moved from very, very few in the 90s to a highly densely populated decentral green energy production. And of course that puts a lot of challenges over the years on the zone balancing. So how we match supply and demand on a very short-term basis. So of course for that we have energy management. We do that on an intraday, day-ahead basis, intraday basis, and we're using these days now also algorithms that can do that in the shortest period of intervals, learning by themselves. And it also saves us money, so we buy, we purchase, we sell at better prices, but also makes the network more stable and more reliable actually. So we're moving much more here into automated balancing based on algorithms. And the last point I would like to conclude with, and then hand over to Professor Monti, is any change that you do in companies is of course underpinned also by culture. So how do you go about it? Because change You have to do things differently. It also impacts how we work as a company, how we live hierarchy, or we want to reduce hierarchy, how we embrace technology, the courage we show. And I just show you a few E.ON principles. The first thing is we do a lot of work, and we've done a lot of work, and we continue this work with energy, clear on vision. So what do we really want to be part of? And we say on a very general basis that we want to improve people's lives. This is not just some consulting bullshit, but actually in a world that becoming cleaner, more sustainable, more engaging with customers, sustainable cities, smart cities, reliable energy supply for industries. If I as a residential customer can produce my own energy, I become more autonomous. These are very valuable things that improve people's lives. So in the context of energy, we have a chance as a company to help drive that or at least contribute to this change. And that's very purposeful. And we fill that with life with everything we do. And without our networks, this change could not happen. The second one is, in business you have to be very clear, or when people are clear about what is the ask of them, what they're supposed to do, they can do incredible things. So you have to be very clear on what they are supposed to do. So that's clarity. The second ingredient, they have to be empowered. And organizations tend to have a lot of approval rights, a lot of processes that box people in. So we're trying to more and more set people free, to give them more freedom to make decisions. But then we're also there to hold them accountable. Because, of course, trust also comes with responsibility. But that's the formula we're trying to work on, which I think is changing. The third principle is very close to my heart because a lot of people, or we all love what we think. We all have wonderful ideas. At the end of the day, what really matters is what you do. Because the world is not in short supply of ideas, but we're in short supply of actually doing. So if you really want to test the culture, it really only matters what you do and not what you say. And my door opens very often and people tell me everything that's not working. I have an overflow of that. That's still in the idea space. So I'm still sometimes thinking, thanks for sharing. I'm glad I didn't know. Of course you know, but sometimes very hard to change. So my message is that when you're in a startup, you're more in the doing space, I guess, than the thinking space. It's really about doing, also for companies. What we're trying to do is when we apply change, like in the grid business, we're trying to roll it out. So we're looking for areas where we can scale. So we have a lot of pilots, but the thing is, how can a pilot grow? How can you actually find a market share that is relevant? How do you have real impact? And we struggle with that. We do struggle with that, but I think we are always honest about that question, is that relevant, does it scale? So that's why it's important that it's part of the core. We try to work on communication because when you do communicate, when you do change, you have to communicate. It's also fair that a lot of people have fear. And being transparent and speaking language from the heart is critical. We're not doing enough of that, but it's something we remind ourselves. The last but not least, what matters is speed, also in whatever you do. The speed is important because that gives you the time to do corrections, put corrections in place. It's also a reflection of how good you are in terms of reacting. I showed you the speed around us when it comes to innovation, also in industries. So for that, in order to be able to react, to compete, you need that speed. And that's why we say 1 month for us is the new year. It feels strange at times, but actually when you do things rather than think, it's actually possible. So I think that's for us also a process, and I always encourage everyone to think about the time dimension because life is endless and there is not much time. There's sometimes not a reason why it should take that long. And that never comes at the compromise of quality usually. So people confuse very easily time and quality. Sometimes when you're able to deliver faster, you tend to deliver also better these days. So there is actually a positive correlation. That's what I really wanted to share as an intro. And I very much look forward to discussing, debating with you later on. So with that, Professor Monti, thank you. You will speak after. Okay.
Thank you.
So the real content will come probably after I've left.
Hopefully you see it.
No. Okay. So I'll do that.
Yeah.
Thank you very much. As we're very agile and we're looking at the tight schedules here today, hope you all guys are okay. We swap the panel discussion with the keynote speech, and we will start with the panel discussion. And I have three very honorable guests here today. The first keynote speech you already heard from Wildberger, the second one, Professor Monti, and the third member of the panel discussion will be Artur, Löwen, the CEO of our startup Gridhound. So we're going to try, I hope you guys have some questions ready as well, because, well, I do. And I'm going to start with a few questions that I've already prepared, and feel free to join in and ask, as this is a unique chance when you can do so. So we started talking a little bit, seeing the E.ON context, regarding digitalization as a whole, and also, of course, the innovation of the grid. So where do you think the grid innovation is standing in the context of energy transition?
I think we made a few first steps, but we are far from finishing the race. Obviously, digitalization is still in progress, and I think that will take at least a few years, if not decades, to finalize that. But once we have done this, I think the energy transition can be managed very well, and we are able for a new CO2-free world.
I hand over directly to the expert.
I want to learn. I think we have to make a distinction. There is because some people could be upset. The transmission is highly digital, highly advanced. The distribution is where everything is happening right now, and there is still a lot to be done to bring the picture that Dr. Wildberger described, to empower the customers, bring it in the system, and find a new way to work with them together. This is a revolution, and that, as you also said before, it doesn't take one day. It is not just a bunch of software. It brings also cultural changes, different relation with customers, and that takes time. So I think we have always to distinguish that the grid is smart. I tell this since the beginning in my class. If you tell the grid is dumb, that's the impression you give, you make a big mistake, because we build the most complex infrastructure that is running right now, and with very few failures in Europe. But now we are transforming the system internally, and that takes challenges and time.
I mean, we're working with you guys together on some fascinating projects, which make some of our customer solutions interact with the grid in a much smarter way. It actually helps if it works society, but it's also better for customers and the grid operator. And I think, as you say, it's a lot to do. There will always be a lot to do, but the importance that we start, and we start on a programmatic basis, so we have a chance to change that. And I keep on saying that I'm extremely grateful for a great collaboration with the Aachen professors, really a world-class institute, and I think we've become so much better in engaging together, working together. I'm also very proud that we have great entrepreneurs coming from that area. So we are committed to make that work. Hopefully we contribute, but we also learn a lot. So I think that's the future.
I guess Artur very quickly answered my second question. If really the grid innovation is already sprinting off, or are we just doing the first steps? So actually, I'm gonna just jump across and just go to the next one. And really, we're talking about smart grid technology today. What does that really mean?
First of all, I think digitalization is one of the crucial steps towards smartness. Humans are smart, but humans also fail. If smart people put their ideas into software and make it right, the software will not fail. And with that, we can build smart grids.
I mean, I guess you can say that in much greater detail, but if I think on a higher level, what qualities would that enable? So first problem is, you of course need frequency stabilization, and you do that today, of course in real time, but in a very rigid system. You could imagine a very stable network on a micro level, where you stabilize in real time with lots of different power sources, so you combine all those decentral assets. That is a very powerful word required actually for a clean world. That's one aspect. The other aspect is imagine that when I learned in physics that it's very hard to distinguish electrons actually in a copper wire. So follow electrons movements. If you can imagine that you can combine electrons with a data package and you send that around, like data packages we see today, we take that for granted. I think all different applications of storage, training, that opens up totally new possibilities. So just two aspects of what digitization of such a grid would mean.
Yeah, I think if you look at smart grid as a term, may have a completely different interpretation in different parts of the world. I lived for 10 years in the US. For them, means finally reaching good quality of power delivery. In Europe, we had very good power quality. We still do, but now we are changing everything around. We want to preserve that quality. So the goal is to give, at the end, the common element is to deliver to the customer the right level of quality. And but for us, if we combine this with the energy transition, that's a very complicated, challenging task. And then another thing I tell my students, I'll be really happy if in the 100% renewable, we have a grid as good as we have today, because the grid today is great. If you look at distribution and transmission in Germany, the average time without energy is half an hour. There is no other business so efficient for customers. Can we do that in the future? This is the challenge.
Just on that basis, so I came back from 1 week holiday 10 days ago, and we went to Italy. No, we love it. Honestly, it's amazing. I love the country. So we're in a very nice hotel. Friday evening, we're sitting on the terrace for dinner, and the light went off. And it didn't come back. With candles on the table, first thing, oh, really romantic. But after 3 hours, we thought, oh, that's all right. And the beautiful thing was, this was in the middle of nowhere, so you had to drive 40 kilometers to find a reasonable place. Then, because of the power cut, the whole restaurant was down for 3 days. So that wasn't right. So I think that probably could also mean smart grid, right? If it's a bit smarter, you may have some food, but it's still fantastic.
Going to the audience, does anyone have a question?
So thanks for the microphone. Matthias Schilcher, Bayernwerk, Regensburg. Thank you very much for the interesting discussion. Just one thing that would be interesting for me. So if we look back at the collaboration of, let's say, many different algorithms, at the example of a stock exchange. So we may observe that those algorithms may produce very sophisticated results, but in cases of bad luck, can lead to very disturbing events. Some example would be a stock exchange crash. So to maintain the reliability of the grid, it would be necessary to avoid such destructive collaboration of the algorithms involved in different consumers or energy sources. So what do you think would be parts necessary to keep different algorithms in different distribution networks and different energy sources to keep them from doing, let's say, such kind of catastrophe? What do you think would be necessary to keep such array?
I think there are two very fundamental differences between trading algorithms and grid algorithms. By grid algorithms, all grid algorithms have the goal of stabilizing the system. Trading algorithms optimize for taking as much as possible without crashing. Sometimes they go overboard. That's part of the concept.
Well, you touch a very critical point. I see the point, and I think the answer is when we think what will be the system of the future, if we start from the customer, we should build that protection internally in the system. So if the focus of the strategy is the customer, that should embed solutions that don't allow that kind of play. But the risk is there. I always say, I don't want, I use exactly the reference to what you say, I don't want the concept of the energy, the future, to bring the craziness of the market to the customers. They have to be isolated. If that's possible, if the customers are out and they're protected, then you protect the system. It's a matter of philosophy where you put the center of your strategy and development.
It's a great question. I'm first of all, I'm not the expert in any of the financial algorithms, so I follow them maximum as an amateur. But my recollection is that although this may still happen on a local basis, a very fundamental event that happened in the past, so algorithms have also included the fact that certain stop-loss situations where everyone starts selling have been prevented. So stability, I think, to a certain degree has been implemented. But at the end of the day, it's a generic question of algorithms making decisions, right? And in any situation where you make decisions, what is the disastrous effect? Network effect, like financial system, may lead to a crash. In our situation, may be that the network is not stable or goes down, a blackout. But also in self-driving cars, and I find that actually quite amazing to follow sometimes the conversations there, just to make my point. If you look at Waymo, which is the subsidiary of Google, whilst we're still talking about electric cars, they have ordered for next year 70,000 vehicles for autonomous driving as taxis in US cities. 70,000. Their algorithms already has about 16 million kilometers of learning, and they will always have situations where they make mistakes. In the worst case, an accident. Those algorithms learn from it to become better. So they have three sensors: a LiDAR, which is a laser, takes a picture of the environment, sonar for the 3 dimensions, and also then ultrasound, and then also a camera to visualize. And they can factor in 500 meters away from what's happening in the car when they detect it, everything in their algorithm. These things become better. Tesla already has 1.5 billion kilometers in the algorithm. So my point is, the same happens actually in the financial sector. The amount of work done with the algorithm to stabilize the system as an inherent ingredient is also growing in that space. Of course, you can always abuse it. So I'm, in that sense, more hopeful. On the other hand, you also need to have strict rules, but I think that's, I guess, the future.
One more? Come.
My name is Dieter Keller-Giesbach, a small utility-focused boutique consulting. The question is going to you, Mr. Wildberger. When we talk about smart grid, and my impression is that the convergence of a data grid and the classical distribution electricity network should work. So I have understood and see that E.ON is also, and the new E.ON have plans to invest into the fiber and broadband activities as well. How do you see this? Will the new E.ON be a heavy competitor of the fiber operators in the future? And how do you see the convergence or the interaction of broadband fiber and the classical electricity distribution network?
So already today in our grids we have 40,000 kilometers of fiber. So we are commercializing that, but we're using that for our own communication. So a lot of our backbone is already on fiber. So we have capabilities there. We see a huge demand in Germany. We see a lack of fiberization. I don't know what the real English word would be. Also, some of the business cases are challenging, and we see that we have, with our contacts in municipalities, it's from an asset perspective, not too different type of business, so we have a lot of skills there. So we're looking into this, and we're also investing into that. It's always been part of our business on a smaller scale, and we're trying to accelerate that. Now, to your question, how much we take on the big guys, look, never underestimate the elephants, Telecom or the Vodafone of this world. So we know our space. Nevertheless, if we can take them on, I wouldn't say it, but we're trying to do that in a modest way. But if you look at the last mile and content, which is also part of the world, where I'd say there is more way to go for us as an industry, because that's not our home turf. So we are looking at, if you look at EWE, we've done that business, also the end business for a long time. Those kinds of models we're looking into.
Okay, as we're running out of time a little bit, I'm going to have the final question to all of the three participants. Is you all come from different areas, and I think that's a very nice combination that we have today. We have a representative of research, university, big corporate, and successful startup. So from this side, talk about grid innovation. From your perspective, from perspective of startup, of university, and the corporate, what is your main contribution, would you say? And I thought I left the easiest one for the end.
Yeah, regarding innovation, I mean, we are a university spin-off, so what we are innovating is part of, has been part of research just a year ago or so. But yeah, I think bringing data science into the power grid, creating a digital twin of the copper is what we bring into the world and what we exploit.
Well, it's hard for me to pick. I mean, we are, as university, we are involved in all of this. So I daily cooperate with Gridhound. I was one of the founders of Gridhound. I have project directly with E.ON since now 10 years. So I think the nice thing of being a university that you don't have to choose. You have the exposition to all the different, and that allows us to have variety of contribution, and don't like to pick one and say this is, the next one is the best one. I think we are working with some very interesting ideas, which I believe will be the most interesting contribution. Maybe for the moment there should be the algorithm Gridhound is using. There's one thing coming out of my institute, but I think the next one in any case is the best one, because there is always something new coming.
Look, I don't personally sit in my office and innovate myself, so my direct contribution in that sense is limited. But I have the privilege to work with an enormous number of great people of all different faculties in our company, with partners, universities, research institutes. And I happen to, with my limited scope, but love technology, hopefully understand it to a certain degree, and use, as long as I have that role, to create an environment where people can make those changes. So my role, I think, is very much that of an enabler. And I do believe that when you want to create change, you have to have real conviction and persistence, obsession also from the top, to create that environment. But unfortunately, I lost my insights from maths or physics to be able to contribute myself. But I'm still awed by what people do, and sometimes they explain it to me.
I think that's a nice note to finish the panel discussion. I think every single one of them.
Another question or no? Sorry.
I do have a question, but I'm not sure. Are we doing time more?
Up to you.
And I have to say, your question was really good as the last one, but maybe you have another challenge.
Oh, well, raises the expectations.
David Meijer, I work for Alliander, distribution network operator in the Netherlands, but also representing Rockstar, incubator program in Amsterdam. What we see in the Netherlands is also cross-commodity optimization. We're very much looking into silos of electricity, natural gas, heat, hydrogen, and so on. To what extent does E.ON see the benefits of commodity optimization from a grid perspective? And to what extent does Gridhound have plans to work on that, and to expand your proposition and to facilitate that?
I mean, currently we are not looking that deeply into cross-commodity optimization, although we are looking into applying our approach to different types of distribution grids, so not only power, but also water and heat.
So we do see the opportunity. I would say we put a toe into the water in this area, but we're actually in conversations with 2 companies from the Netherlands on that topic, because I think you are more advanced in that space. We talk obviously on a high level what we call sector coupling, which is a bit different, but you can also do that on a smaller scale. So we're looking into it, but I don't think yet we have a real business model, but we believe in it. And we see that in action to a certain degree, but it's not yet as fundamental as our principle. But it's good to learn also from other countries and other markets.
I have a quick remark about E.ON. So 12 years ago, E.ON created the E.ON Edge Research Center at my university. They made a SWOT analysis of our university, and they created the new advanced chairs that should be added to the faculties. They came up with my chairs, looking at digitalization of electricity 12 years ago. And my neighbor is Professor Müller, energy efficient builder indoor climate. And they told us 12 years ago, you guys should work together. So there was some forward looking there in this direction, definitely.
And have you worked together?
Yeah, we work together. I mean, we are
watching.
We are very much, I think among the chairs in the center, the EBC and ACS, these 2 chairs are really sometimes so integrated it's hard to see the boundaries. We have offices shared between the 2 chairs. We share the software developers because really we see the value, because at the end if we focus on customers, that's where these things come together. So if you start from the customer, you have to look at cross-commodity. It's necessary.
Thank you very much. Thank you all for participating. It was an absolute pleasure to give a chance to the audience to ask some questions, and of course have an opportunity to ask some questions myself. I also can agree to the same thing. I also learned something. So I guess that was a win-win for everyone. Thank you very much again. And on that note, Professor Monti.
Yeah. Oh, yeah. Yeah, works. So my task here this afternoon is to give you an overview of the ADMS project. As you know, this event is the last public event of our project, and I will try to give you a summary of the work, then later other presentation will enter more into details. My goal is to give basically an overview. And I think we have to convince you of the story of goals of the European Commission on decarbonizing the energy system and increasing the penetration of renewables, and ADMS fits in this picture as one of the projects that is delivering products for future grids. We have been talking already, thanks to the presentation of Carsten, I can go quickly about the main introductory topics and try to focus on the content of our project. So the bottom line, where we're looking at to give solution for grid awareness, predictive tools to actively manage the grid in real time. I think the critical part is this real time part in the definition. And we have increasing renewable resources. We have the need then to dynamically monitor the grid. This was a topic that has been growing very rapidly in the last few years. When I started my chair, we were immediately looking at grid monitoring. And the first time we were talking with experts, they couldn't see really this coming. It took years before the need of monitoring became quite evident, and first came covering the medium voltage grid, and as we do it here in this project, the last development is that also low voltage are now part of this picture. There's been a picture evolving very rapidly, and ADMS has a task to increase the network stability, increase the grid capacity, increasing the penetration of renewables, and it's all in the picture of the 2030 target of the European Commission. It's a 2-year project, so that was a challenge. It's not as many programs in Horizon 2020 taking 3-4 years. And the reason is because the project comes from a specific goal, which is called Fast Track to Innovation, which is not supposed to deliver new research, but to take the research out of the universities and bring it into life. Final implementation ready for commercialization. And then obviously make sense of this is a fast process. And we are 5 partners, RWTH, coordinated together with MAC from Ireland. Then we have ALTEA, Gridhound, and Università of Bologna. So we have basically 3 small and medium enterprises and 2 research institutions defining our consortium. And yeah, all of us bring significant expertise. The university in Aachen is mostly being focused on the 2 elements, as we'll show you later, in monitoring algorithm, working together with Gridhound. As mentioned before, Gridhound is a spin-off of my institute, but also developing new solutions for measuring technology. Particularly, I'll have some element that later describing what we call the low-cost PMU. University of Bologna has a long tradition in measurement technology for power systems, and actually they're very much connected to ALTEA. Basically, Professor Peretto sitting here has a double head somehow. ALTEA is a very successful story in sensor, particularly in the medium voltage area, and MAC covers vice versa more the low voltage part. So that we bring this together, we had the possibility to cover low voltage, medium voltage, going from the copper, and thanks to Gridhound, to the cloud. So Gridhound then becomes the head over integration of the platform concept. So what we have to do as a fast track to innovation means we bring this expertise, we integrate them together, and we come to product. So then we have to be product, the project ends now in October. That means that the target for the Commission that we are ready for commercialization 2019. We demonstrated this because, as I show you, we are not just working in laboratory, but we had the opportunity to do field tests with significant utility across Europe, particularly ESB network, which will be later connected to us in the top row. That's what I was in the schedule. It's not working. Oh. Anyway, we'll have information definitely on the ESB trial from our colleague from MAC. We have Enel e-Distribuzione, where we had one field test in the region of Emilia-Romagna, close to Bologna, where the university. We are doing things in our own campus. We are not just doing research on smart grid. We want RWTH to be a smart grid. RWTH is his own distribution grid in medium voltage and low voltage, connected to the grid of Aachen clearly, but we have our own monitoring systems, and we are working together in the university with the asset management university to make our own infrastructure better. And last but not least, we have been working also with Bayernwerk nets in Germany. Yeah, here is just to give a physical interpretation, geographical location covering north of Europe, more Central Europe and the south of Europe. So also from that perspective, the project is quite broad and covering different use cases. And the main points of the concept is to have sensor deployed, two different types in low and medium voltage, then bringing the data directly into the cloud, and having in the cloud advanced algorithm for monitoring. That's mostly the contribution of Gridhound. So bringing a complete network management systems and having then an open platform where new services could also be developed and deployed after the end of the project. So we have a complete architecture that is running. We have some of the services running, but as we'll show you, we are also going forward. I have at the end of the presentation reference to a new project where all the parts of the ADMS have been invited to join to make the next step an even more complete concept platform. Yeah, here is all the ingredients together. Starting from the RWTH contribution, we built, deployed, and demonstrated working a low-cost phasor measurement unit. Phasor measurement units have been in the market for many years, but have been famous to be a quite expensive component. So that maybe transmission system operator have been investing, but distribution was not a market for PMU. But we think there is a value for PMU in distribution grid. For that reason, we have to bring down the cost significantly. And that's what we have been doing in our university. This is our first prototype, the one that being deployed, which brought down the cost significantly. We are building a next generation, integrating this component in a single board and cutting even more the cost, so that we get to a very low cost device and developing appropriate software that in any case could be ported also to other platforms. So we are able to build very efficient software, bringing the good qualities at a very low cost. You have to keep in mind that in distribution grid, this is particularly challenging because we have a very contradictory set of requirements. On one end, we want to cut costs because you need more devices, because the grid has more nodes than in transmission. So per unit of kilometers, if you keep similar ratio, you need more. And then you want low cost. On the other hand, because the distances are way shorter in distribution, the system has to be more accurate than what is in transmission. So if we build a PMU following the requirement of the standard, we build something that doesn't have real value for the distribution grid. Because when we talk about angles and the distance are too short, or the angle is really accurate, or the information has no meaning. So that makes the development of those devices particularly challenging because you want to be better than the expensive one. And luckily we had an history on that device, long term. We had a patent. That was one of the contributions to the project that was developed in RWTH together regionally with the University of Cagliari, where one of my assistants, Andrea Angioni, was working before. And we brought it down also from the hardware point of view. And this device is now installed in various grids. What I'm really proud of, beyond the ADMS project, we got other European projects calling us and saying, we know you have a low-cost PMU, we want to install it in our project. Could you deliver one more? So we are becoming a production facility of PMU, which was not expected. But in any case, we have all the critical ingredients of a PMU in a small box and extremely low cost. Right now, this version has a total cost of 300 euro, but the new one will be more in the range of 100 euro. So that brings, compared to the several thousand euro cost of commercial PMUs of today, it's a dramatic change in the cost of the device. And this data are being collected. This is playing directly from our grid. So sending the data, the PMU are connected to 4G networks currently and delivering data to the cloud. We are collecting our data and monitoring our own grid. For example, these are some of the data from our grid, we are able to look at voltage, magnitude, and phase, look at the frequency, signal, having measurement of rate of change of frequency available locally in our distribution grid in Aachen. And then those data can be the ingredient and also help the higher level part of ADMS, which is the Gridhound platform. The Gridhound platform is a completely new way of looking at state estimation. So far, state estimation we consider a highly mathematical tool. You have a model, you invert the model, and you extract the solution. What we come up with at the moment is much better than no picture. And if later I add sensors, but I don't wait the large investment to start learning about my system. I think this is the key element of the solution that the Gridhound algorithm is bringing, using data-driven and machine learning to solve a problem that classically was solved as the deterministic solution of algebraic equation. And this is the full process. Obviously, we need to start from a digital grid model. That's not always available. We are now developing a new step on this direction. It's okay, if we're starting sensor, we use the sensor to learn about the model, we tune the model, and then we go back to the grid. So the criticality of determining where you put the first sensor helps you also stepping the lack of knowledge you may have internally. This is something we are developing right now in cooperation with a new project. And then we can do a lot of simulation. We developed in RWTH an algorithm that makes the solution of power flow extremely faster than any other solver in commercial solution, much more stable, designed for distribution grid. And thanks to this, Gridhound can run thousands of scenarios in no time and learn data that are somehow fictitious, if you like, but they're generated according to a model you can train and continuously educate with the sensor you already have in the field. From there, then the machine learning can learn. But the nice thing is that you generate more data than what you have in the system with this process, and then allows you quickly to have something that can be deployed in the field and give you meaningful results. Then in the long run, you learn, continuously improve. As Dr. Wildberger has mentioned, the nice thing of this machine learning system, they get better by themselves anyway. But we have a process that makes them really good to begin with. This was fully integrated in the RWTH demo, where we placed several of the PMU for some in medium voltage, some in low voltage. So we use both the sensor from ALTEA and from MAC. We integrated them, we brought the data to our internal cloud system, so we're able to verify the complete value chain from the sensor to the cloud directly in our field test. And here you see some of the picture. This is the connectors from ALTEA. Here the MAC unit, and this is the low-cost PMU, the three hardware components of the DMS solutions, and they're placed in different parts in our campus in Balaton, and is currently running even right now. Here a little bit more insight for the medium voltage setup, where you can appreciate the component from ALTEA, the medium voltage terminators, sensor, and their connection to our low-cost PMU, the very, very first prototypical version of that. And this is all sitting in the secondary substation of our university close to our building. And here we are inside our building, and that's the low voltage part of our grid, where we added the connection of sensor from MAC, and again another of our low cost PMU, so adding the old devices also in the low voltage part. Similar activity have been done in the Irish demo. This is the substation as was used, where the sensor from MAC being installed, and we are deploying tools also on the smartphone, and it was an incredible. I'm sorry that ESB couldn't be today here, because I heard from them directly saying, we learned so much about our grid just running a field test, like significant imbalance among the phases and large peaks in the power profile that we're not aware, and losses that could be significantly changed, being aware of how the loads is moving. All that simply with a small field test. That says how much you can learn from few sensors inserted to the grid. Then we went to Italy. Unfortunately, I didn't, but some did. And we installed in the Enel solution. What is nice about the Enel field test, they already have a lot of advanced solution in their substation, but we were able, collaboration with the University of Bologna to add our solution on top of their ongoing architecture. So Enel didn't have to change their architecture to integrate the ADMS concept because we added electronics that was coexisting with the solution already deployed. Basically, all their secondary substations are fully equipped with smart devices. So at the beginning I thought, how can we work with a company that's already so ahead in the deployment? But thanks to cooperation with Bologna, we integrate perfectly with the Enel, and also their data are integrated with our micro PNU, and we added the cloud connection they didn't have before. So it was a seamless integration. It was one of the great results, I think, in our activities. So we are bringing this key innovation, distributed sensor networks, thanks to patented flexible magnetic sensor, the micro PNU, the power quality monitoring capability, low and medium voltage, an innovative solution for network management based on artificial intelligence, and a coherent picture that builds ADMS as a platform. And for all solutions, we always follow the communication international standards, so that's how it's possible to seamlessly integrate in existing solutions. Yeah, so the benefits, I basically already mentioned through the description: more knowledge and support for renewables, more cost-effective action, and at the end, all that through low-cost solution. Everything we did is way cheaper than what is currently in the market. And then we are ready for a mass deployment. Hopefully we hope to have more activity beyond the project. The project was very successful, but now is the challenge. But like I said, this was very convincing, so that we convinced a bigger consortium that was developing a new Horizon 2020 proposal, which is called SONIA, and the whole consortium has been integrated. SONIA is adding a new dimension to bring the innovation more in the IT side, because the key innovation of this project is to use more virtualization of the automation, so making the extremely low-cost hardware installation in the substation. Basically, once the data is digitalized, should leave the substation. And using edge cloud, we can bring the automation to the edge, close to the substation, but doesn't have to be as custom hardware when we run the algorithm. So that reduce even more the investment in hardware utility have to do, and then more moving into service. So in the vision of offering automation as a service, which offer a completely new business case in which a company that owns the SONIA solution could offer smartness to any utility around the world, sort of Airbnb of automation, if you like. You go with a software that is totally virtualized. In the substation, you need only the digitalization part. And the algorithm used are the one developed before in ADMS. So we made a transition in the IT quality, if you like, in the architecture IT, and using things like edge cloud integration and possibility in the 5G solution. Ericsson is the coordinator, not by chance. And understanding how 5G bringing edge cloud could be one way, but edge cloud can be deployed also not with 5G. So we shouldn't see that as a necessary architecture. The edge cloud is the solution. Edge cloud can be deployed through the 5G, but can be deployed also with other architecture. That's the architecture as depicted by Ericsson. The nice thing of their solution is that they bring the network to the edge, and that makes the communication extremely secure. Your data don't go through the internet to reach the intelligence. This is the key part. There is a breaking of the communication path. The data before, if you were sending, as we were doing before, through the 4G network, they first go to the classical internet, then they come to your automation. Here, we skip that route, and that's the key element that makes edge cloud interesting for the automation, that makes the delay and reliability of the communication extremely higher, so that we can imagine also to close the loop through the cloud, which was not possible before edge. Yeah, that's basically in summary what ADMS is about. Then my colleagues will give more detail, but obviously I'm open for first question that maybe you have to understand. Thank you for your attention.
So we continue, and Thank you very much. First of all, again, we're going to continue, and we're going to talk about key standards for effective smart grid management. And I would like to invite Professor Peretto to the stage.
So before starting, I can say that dealing with standards, presenting all the standards relevant to smart grid in 10 minutes is well beyond a challenge. So it's almost impossible. So when I've been asked to have a presentation relevant to the key standards, I had two choices. The first one was the simplest one, to just scroll down the list of all the standards, completely meaningless and nothing to say on that. The second one was to focus the attention on some that I personally consider very important to present to the audience relevant to the standards. The last comment as an introduction, I want to say that we have to make a distinction between standards and documents. There are tons of documents provided by EU, prestigious bodies like universities or other entities, dealing with how to build a smart grid, how to control, to operate a smart grid. On one side. On the other side, we have standards. Standards, as you know, they are mandatory. We need to follow them. Everybody has to base proper application and installation on those standards. So I preferred the second choice, and I prefer, after surfing and searching and collecting all my information I had, I came to the conclusion that today, in my opinion, is better I present the most important document circulating among Europe, but it is somehow copied by RWTH as well, so US side. And before presenting it briefly, I just introduce the concept of standardization in Europe, as I suppose everybody knows. In Europe, we have three main bodies concerning standardization. They are CEN, European Committee for Standardization, the CENELEC, Committee for Electrotechnical Standardization, more focused on our task, and the ETSI for the telecommunication standards. Also, this last one belongs to the smart grid because, as you know, communication is getting very, very important during this period. In 2014, starting from that period, more or less 13, 14, the three most important bodies, they consider that these one are taking standards coming from IC, some from NC, and so on. But they are the official bodies providing standards for smart grids. And in 2014, they built a group called the Smart Grid Coordination Group. And this group wrote some reports, some documents. One of them I will present now is very, very important. It's, let's say, the Bible, very important for the smart grid operation and control. The reports mainly concern the extended set of standards of support for smart grid deployment. This is what I would like to stress today with you. The second report is an overview of methodology, and they presented the SGAM approach, for instance, and so on. The third one is the smart grid concept, examples, case studies, and so on. And the fourth one is the smart grid information security. Coming to the first one, this report is divided into two separate reports. The second one deals entirely with the security. So indeed today, let's say, it's less important for us because I would like to concentrate our attention on the first one. The first report is a very big report, almost 300 pages. and proposes an updated framework of, I have copied it from the scope of the document, I have put it in this slide. An updated framework of standards which can support the smart grid deployment in Europe. It provides a selection guide setting out the relevant set of existing and upcoming standards to be considered, and explains how these are able to be used and so on. What's important, it is not a list of standards. Yes, there are a few pages, let's say 10 pages dedicated to the list of all the standards. But this document is very important because it explains how to use the standard, where to use. Now I show you some examples. This is the document, and if everybody, this one is the last version, 2017, because it started in 14, then a new release in 16. Now we have, this one is not official, it is under review, but I prefer to present it today. If you want, you can download it from this website, so it's completely accessible to everybody. And this is the front page of, and you can see Smart Grid Set of Standards version 4.1. And I would like just to summarize what's inside this document. And consider that it includes all standards dealing with the smart grid, all, from communication, everything. And it is divided into 9 sections. The first ones, 1, 2, 3, and 4, are relevant to definition, scope, and so on. What's very important is the pointer is there important?
There. There you go. Yeah.
This one? Ah, okay. As you can see, the section 8 is the most important one because it deals with the practical application, how to build a smart grid, which standard I have to use for implementing and operating a smart grid. And it is divided into transmission, management, distribution, then there is a section devoted to energy resources, including storage, then another one relevant to smart metering. And regarding distribution, I concentrate on this today. There are some subsections relevant to substation automation, feeder automation system, and then we have also power quality systems, not only measurements but also analysis. And then ADMS, Advanced Distribution Management System. Other sections are relevant to demand and production, e-mobility, and the microgrid systems. Then sections 7 and 9, the 7, The 7 shows the SGEM approach. I don't know if you're aware of it or not. However, it is the basic framework, the smart grid architecture model. It's like a 3D dimension, no? Where a smart grid can be seen in different ways. I show you here now an example. And section 9 is with telecommunication, security, and EMC mainly. Power quality related to EMC. This is an example. I selected, for instance, the feeder automation system, and the system look at the SGEM, according to the SGEM approach, the feeder automation system is divided into type from generation, transmission, distribution, distributed energy resources, and so on, and the process, field, station, and operation. This is the division. How a system can be seen, and you can check and verify that in the process you have the generation, you have the customer side, you have medium voltage, high voltage, and so on. In the field you have intelligent electronic devices. In the station, the remote terminal unit mainly, and then you have a connection to the operation and control room. Sorry. And for every kind of, let's say, topic, in this case we have a feeder automation system, the document presents the standards pertinent to that, relevant to that. For instance, in this case, we have these standards dealing with the sensors. We have 15 standards relevant to instrument transformers. So if you want to build a smart grid, you have to start from the sensing element, and for them, you have to base and to install them according to these standards. So the document teaches how to use standards according to the application. Then, for instance, other standards are here. The 62 to 75, 71, I call the switch gear, control gear, and digital interface is based on communication 61 and 50. These are examples, but they are present in the document. So if one reads it, can understand which are the standards based its implementation. The second one is the feeder automation system communication layer. And in the communication layer, say communicating between the remote locations, the infield and the control room, you have to follow and to implement, to use, to base your system according to these standards. Almost all of them based on 61850 protocol. The communication between the field and the operation is according to the 60870 or 61850. I have here added some description of the standards, all relevant to communication, and here the same. And the third one, and the last one, is the information layer. The information, how to interpret data, how to collect them, and how to calculate values, and so on. And it is done, must be done, according to such standards. Here again, I have added some explanation, very summary of explanations. However, in the document, you can read the description well done, and well understandable, not difficult to understand. This is a screenshot of after all the description. You have the pages I told you before. There is a list according to the SGAM approach, information layer, communication layer, and so on, and all the standards with the note describing the meaning of the standard. So this is just a screenshot, but there are a few pages including all the standards. And very few words relevant to the advanced metering infrastructure is another very important section in the document. The metering infrastructure is very important because it is not only related to the measurements and the interpretation of measurements, but also the use of measurements for controlling the network. So in all these parts you can read both sections relevant to indexes, parameters to be measured, and also the use of measurement for controlling network. And this is just a sketch of taken from the document, dealing with any. You have neighborhood, network, layer, local, let's say user, and then you have the control room with the display, with interpretation of data, and so on. So just to summarize, I wanted to bring here today what's considered the most important documentation for including collecting all the standards relevant to the smart grid. I think that this one is of paramount importance because a utility or private customer that wants to build a smart grid or smart grid concept has to follow this kind of standards. Standards are mandatory, so we have to use them. And here you can find the complete set of standards made by standardization bodies, not by other entities. And that's it. If you have any other question, here. Thank you.
just giving what Wildberger was talking about. And there is another dimension of standard that is evolving, which is more customer-centric and more less grid. What you present is fantastic overview grid. And currently, the European Commission is developing an activity, it's a document that I would like to coordinate for DG Energy. It's called COSMEG, Comprehensive Smart Grid Architecture. And the idea is to understand how from the grid you include the customer and you bridge to other sectors. Because right now, the IEEE and all the activity have been developed as electricity silos. But if you want to build link at the customer level, there is a complete new dimension of data management that is not part of the activity IEEE is interested in, so they are not covered. But the Commission sees that as critical to build a data economy in which energy is one of the vertical, but not the only one, and how this vertical is integrated with other vertical, like mobility and so on. And this document will may discuss in a big meeting in October, and then will become public. And it defines some guidelines on how to move from silos-oriented data management to an economy, data economy, going beyond electricity and looking at customer premises and so on.
So it will be a guide.
For the moment, it's only a guide that I'm coordinating with many stakeholders, and then we'll be discussed in Brussels, and then will be presented as a guide, and then we'll drive some of the next round of projects in the Horizon 2020, and then at the end it should become an ETSI standard. That's what I think.
Wow.
So it's a different dimension.
So relevant to the communication, ETSI.
And data management, so data modeling, how the data modeling of electricity is merged with other data models to build things like smart city, for example. You need to cross from IEEE terrain. So that's why I thought it's different from what you present, but I think this may be interesting for some other people to know that this is
when it will be included, they will the set of standards. Yeah.
Should, maybe.
Good.
Thank you. So we're going to go directly to the next speaker, and she's going to talk about sensors in smart grid management. Elisa Scala, thank you.
Hello everybody. I tried to create a presentation regarding sensor aimed to help the smart grid management, because I'm working in ALTEA, so I develop sensors for 10 years, around 10 years. So I tried to focus on the peculiar features that can be relevant to the smart grid management. Just to recollect very quickly the main technical aspects of the smart grid. From the electrical point of view, it can be considered a big grid made of multiple sub-grids that can connect the producer and consumers. And to make it smart, there were introduced electronic, IT, and communication that link all these sub-grids. The purpose is to get to an enhancement of the performances. First of all, the flexibility of the grid and of the grid management, reliability of the service, efficiency of the grid distribution in terms of efficiency of the energy distribution, and the management of peak demand due to the fact that the use of the energy is changed in the last times. To reach these targets, a smart grid should implement some functions. Here there are some examples, but I think the most important are in the next future, the self-healing, the high penetration of the intermittent distributed generation, high power quality. And to get to these implementations, in practice, what we need is automation, control and measurement but made in a remote way. So a very also distributed monitoring. The functions that are mostly implemented thanks to remote automation and measurement are, first of all, the fault location, the isolation of the fault, and a fast service restoration. Then another very important parameter is to monitor the rate of change of frequency in the network. Another important target is to control the distributed generation. That means not only to monitor, but also to control their intervention in the network. Thanks to remote measurements, we can have a more capillary awareness of load profiles that will help also in the management of the grid. And other two key points that are, on the basis of our experience, are very important for DSOs are to monitor the power quality and to monitor real-time diagnostic that should help the DSO to plan, to schedule the maintenance in the grid without having to intervene when the fault has already occurred. In this scenario of a smart grid management or going towards smart grid, in the last 5 years, new technologies have replaced measurement transformers. The benefits of the so-called low-power instrument transformers are several. First one is that sensors, respect to traditional transformers, are very light and compact. Another very high benefit is that they can be embedded into other equipment that is already available in the substation. And this helps a lot in retrofitting. They are safer in the sense that there are some phenomena in the measurement transformers that are not present at all in new technologies due to the fact that they are based on different principles. And their outputs are very, very low, maximum 1 volt or a couple of volts at rated voltage and current. That means they are safer intrinsically, and so there's no need of additional protection equipment as it usually happens with the measurement transformers. Another key point regarding new technologies is the very wide dynamic range, in particular for current sensor, because in this way one device can cover both protection and metering application. They are cost effective due to all the other features. Here I put some examples of companies that in the last 10 years worked on LPET. Then we come to the technical features. That means which are the technical features for a so-called sensor that is a low-power transformer that enhance the smart grid management. The accuracy is very important because, for example, for PMUs and for state estimation, the minimum accuracy class required is 0.5, but actually 0.2 is recommended. Whereas for smart meters, for revenue metering, and for some advanced protection functions, such as, for example, the computation of residual voltages and currents on the basis of direct measurements only of the phase parameters, we need at least 0.2 or even better. But this accuracy class has to be maintained over a very wide range of temperature. That means in indoor typically is -5 plus 65. In outdoor the minimum is -25 plus 65, or sometimes -40 plus 65. And also the accuracy class has to be guaranteed in compact three-phase enclosures. That means that all the sensors have to be very immune to other sources of electromagnetic fields. And it is a challenge. And last but not least, large bandwidth. That means that for different applications, we are required to design sensor with a large bandwidth. For example, the minimum requirement is for special quality metering, where we have to go to up to 3 kilohertz. Otherwise, we can have requirements to have a very large bandwidth in low frequency to monitor motors, or in very high frequency, such as 150 kilohertz to monitor inverters for power quality purposes. And coming to partial discharges and fault location, we get to a bandwidth that goes from 100 of kilohertz to megahertz. Here, there are some examples of installation in indoor substation, 24 kilovolt. I wanted to underline that all of the technical features that were shown before has to be also integrated in equipment that grants other requirements that each DSO can ask. For example, most of the DSOs want galvanic insulation due to safety reasons. And also they ask for low impact solution because they need to install the sensor in already existing architectures. Reliability is required to be very high, and sensors usually are also well seen to be multi-purpose. That means that can be used for metering and protection, but also at the same time for PD detection or for fault location. And in the last 2 years, we were also required to host other sensors in the same body of voltage and current sensors. That means, for example, temperature probes for diagnostic purposes, or voltage present indicator capacitive couplers. Then there is the requirement on environmental compatibility, because for outdoor installation we need a sensor that have to be equipped for heavy pollution level, to grant IP level, that is protection against water, dust and so on, resistant to UV, resistant to salted fog, and that passes all thermal and aging stress. That is all the type tests that are usually performed on post insulators for indoor and outdoor. This was an example of a combined sensor installed in outdoor enclosure, and this is a voltage sensor in outdoor enclosure. These are other sensors, combined current and voltage, that were developed to be embedded in medium voltage cable terminations. That means on the left you can see air insulated termination, and on the right you can see plug-in connectors. Both of them embed voltage and current sensors. And also companies are pushing a lot the sensor embedded in equipment that is already existing in the substation, that is bushing, post insulators, and back plugs of different shape, of different profiles. This is just an example to give an idea of how it is installed. So what's next? We know that in next year, E-Distribuzione, that is the Italian DSO, will start the installation of low power instrument transformers also in primary substation, whereas in a secondary substation they already installed sensor instead of transformers. Presently, the ISC is working on a new standard that is relevant to sensors embedded into existing equipment, as I showed previously. So not standalone sensor. And another challenge is that accuracy requirements will increase because there are high-level metering applications, such as the calculation of the residual current and voltages on the basis of the three phases measurement, the PMU's implementation in distribution grids, the evaluation of electrical losses, power losses, and the detection of faults which have high impedance, that means very, very low current. Thank you.
Any questions? No. Okay, we're gonna do a very short 8 minutes break, 5 to 3. We all come back here, so now I have time to get some refreshment, relax, and then we're gonna proceed. Thank you very much. So we're directly going to go to the second part of the presentation of Elisa Scala, experience from the field.
This presentation quickly will make an overview of the field trial of ADMS in E-Distribuzione distribution grid. So the ADMS field trial is running in E-Distribuzione medium voltage distribution grid, and in particular in an area located nearby Forlì town in Emilia-Romagna. The area is quite rural where the ADMS field trial is running, and is towards the mountains. The architecture for this field trial, as already anticipated by Professor Monti, is a little bit different because in E-Distribuzione substation there were already installed RGDM and smart termination. That means sensors embedded into the cable termination and designed and produced according to specification issued directly by E-Distribuzione to be connected to RGDM, that is an IED for both measurement and protection. And so we had to add one electronic device that we call splitter in order to get the same signals of voltage and current sensors to be given also as input to the low-cost PMU, but maintaining the calibration of the system in both ways. The purpose of this trial is also to, on the one hand, to get the data from the low-cost PMUs and to evaluate the phase shift between nodes on the same grid in order to then implement power flow and state estimation. But on the other hand, to collect the data on the three phases by the RGDM on the Enel e-distribuzione data network, in order to implement, to try an algorithm written at the University of Bologna that wish to estimate the phase shift without getting simultaneous measurement, that is, without the synchronization by GPS. The 6 PMUs that are used in this trial were already tested in laboratory, both for communication and for calibration. And here we can see a generic representation of the two lines on which the ADMS hardware was installed. There are two lines around 10 kilometers and 13 kilometers. Both are mixed lines, that is underground cables and overhead lines, 15 kV. This is line 1 and line 2, just to give an idea of where the equipment was installed. The first installation was made on May 10th, and we covered the first line. That means we installed 3 ADMS. And here you can see the hardware, that is the RGDM, our equipment, and the UPS to provide power to our equipment. And here you can see the additional antenna, GSM antenna for our system, and GSM very tiny. But then we had bad surprises because we faced issues. Because even if in laboratory everything was working very well, then on field we could find difficulties because the RGDM measurements were affected by errors, and so the residual currents and voltages increased and revealed the errors. Then the PMU acquisition in terms of samples was a non-sinusoidal waveform. And also in several substations there was a lack of communication due to the lack of GSM signal. So, in order to go for the second installation, the solution that we could implement in 0 time were the revision of the conditioning circuit, that is of the hardware in the splitter device, a stronger electromagnetic compatibility of all the equipment, to provide different 4G antennas, and eventually SIMs with different operator. The bad surprise that we had in the second installation day was that we discovered that the auxiliary power supply was completely isolated from ground for safety reasons, and this was not noticed in the first day. Here is, you can see the smart terminations, and here it is the equipment installed in replacing the splitter. And here, directional antenna, directive antenna, all the modification that we could implement. So in July, we completed the activation of the MS. Here there are examples of the signals that now are being collected by PMUs. For example, here we have PMU number 4 over 3 hours, where we have voltages, currents, and the frequency and rate of change of frequency. Then the same PMU over 5 minutes, just to zoom a little bit better on the signals, on the paths. And the same data can be also interpreted as sequences, in terms of sequences, and for statistical analysis. And here we have a comparison of the data collected over 5 minutes from two PMUs belonging to the same line, because obviously the purpose was to compare the results on the same line to check if the phase shift was correct. And here we have the phase shift between the two PMUs over 3 hours, and we can state that the values are consistent, makes sense, because they are consistent with the length of the line. Thank you.
Thank you very much. The next speaker, John O'Flaherty, please join me on the stage.
Good afternoon. We were hoping to have a presentation by ESB Networks by Skype to give you details about the pilot, but I'm afraid we couldn't get the link working. So I've included a short description of the Irish pilot, nothing as detailed as the research. So anyway, to begin. My name is John O'Flaherty. I'm the project manager of the ADMS project. And as Professor Monti explained, the purpose of the project is really to get the service from the labs to the market. So what I want to talk about for the next 10 or 15 minutes is how we're starting to deploy the service through using pilots with utilities or DSOs into the market. So that's the focus of my talk. So I'm addressing it very much as utilities and distribution system operators who might like to run pilots. So I'll begin by looking at the problem that Professor Monti mentioned about distressed grids and how active distribution management can address that. And in particular, the solution that we, the ADMS partners, can provide in terms of pilots to utilities. And I'll finish up with a brief outline of what a collaborative pilot would look like, or looks like. So to begin, the stress in distribution grids are caused by increased renewables, such as wind and MV and photovoltaic and LV. And new demanding loads such as electric vehicles and smart heating systems. So the result of that is it's stressing the grids and the assets in the grid, and this gives rise to two problems. You've got to reduce your capacity to ensure there's no problems, and you can avoid outages. So what's required is grid awareness, which requires real-time data, analysis of that data at both NV and LV. And this is based on a report that came from Euroelectric many years ago. The passive networks would be your traditional static grid, where you've fixed distribution, you have fixed generation and fixed loads. We're now with smart grids moving into reactive networks, which what tends to happen is you increase capacity to deal with potential problems. And this gives rise to two problems. You have unused capacity, too much capacity, and you will have outages. So what we want to do with ADMS is go to an active system where you can dynamically, in real time, tailor your grid to both the loads, which are changing and they're demanding, and in particular to the distributed generation particularly from renewable energy sources. So as you've seen, this is the ADMS system here. And what it does is it integrates into one system a smart network management system, the Gridhound system, and a deployed distributed sensor network using sensors from ALTEA, as Elisa was just explaining, and from MAC, our power quality and smart grid monitoring systems. And this gives an integrated active solution. Now this interworks with utilities' existing distribution management system, but what it does is It puts the operators as human in the loop. So you can have a smart management system at both MV, and particularly at LV, which at the moment in most grids is very little monitored. And in particular, a very important issue is our solution is low cost and scalable. Because as mentioned earlier, it has to be low cost because there's a lot more monitoring points required. So we are providing an integrated solution of the distributed sensor network with ALTEA's sensors and our smart grid, our grid-wide smart grid monitoring systems, network management system from Gridhound, and this has been integrated by the research teams at RWTH and the University of Bologna. So now, to deploy the system, what we can offer is one ADMS collaborative contract. And in particular, to implement that as a pilot, it will include the services from ALTEA, Gridhound and MAC in a seamless way. So you've seen this slide. So we've got the sensors from ALTEA, the analysis and state estimation from Gridhound, power quality monitoring from MAC, and the research and technical development teams at the universities. Our value proposition that we propose to utilities and to TSOs is that our active distribution management gives you, on one hand, reduced costs and outages, because you can have less wasted capacity. And this means you've increased capacity and service quality. So you can have both ways. And what we do is we provide data and analysis for your existing backend system, your existing management system, so you get all the real-time data you require for your data analytics and so on. And also to inform your field staff of potential problems, so they can deal with it for your outage management. And we're providing this grid awareness at a low cost, so that you can mass deploy it right to your grid edge at both medium voltage and low voltage. So as we say, we can take our grid to be a smart grid in one contract. So that's how we're looking to deploy the ADMS system. As mentioned earlier, we've had experience of 4 pilots in the project. So I'll deal briefly with the ESB networks. As I said, we'll have a slightly more elaborate discussion. So I have just 2 slides to outline what we did in Ireland. So the first pilot, we were looking at low voltage capacity management. And this was located in Burr, a town in the middle of Ireland, where ESB networks were running testing an advanced storage management, storage heating system. And they wanted to see what impact that would have on the local grid. So we monitored 2 power transformer stations here in the town. And what we found was that the load balance was a lot more dynamic than before the heating was put in. And you can see it in the graphs and so on, but you can see them there. There was much greater peak demand because the smart systems tended to come on at much the same time. And this gave rise to higher neutral current returns. So there was an issue there that the ESB had to deal with. However, they were able to keep their voltage within the regulatory limits. So they learned a lot, but they didn't have any major problems. The other pilot, we were looking at outage management at medium voltage cable networks. And we did that at 6 sites across Ireland. And what we found was that we could successfully detect both permanent and intermittent time peaks faults, which was the whole purpose of the exercise. And that this could be done on a low-cost basis. So the ESB could actually now look to putting these sort of monitoring points throughout their network, their substations. And in particular, that the sort of information that was being fed back to the cloud would provide them with information for fault location, isolation, and restoration, which is a key issue. So, in the Sonia project that was mentioned, what we're now doing a further pilot is to actually speed up the supply restoration. So it comes into sort of instead of minutes, it would be fractions of a minute. So what we're doing now, as Professor Monti mentioned, the whole purpose of the project was about fast-tracked innovation. And of course, innovations only make sense when you deploy it into the market. So what we are now focusing on, and have been focusing on, is to deploy this into the market. And we've been doing that by expansion of the existing pilots, all of which are continuing, obviously commercial sales by the three commercial companies. Songyo project, as Antonello explained, and we're also involved in EU SME events, such as the EIC Innovation in Berlin next week. We've also been involved in the Free Electrons Accelerator and suggestions with agile events such as today. So these are examples of the pilots that we're doing and starting. And what we want to do now is we want to do more collaborating pilots with collaborating DSOs. Maybe that's the purpose of my talk, is those of you that want to do such pilots. But we'll consider a minimum collaborative pilot, which would make sense both commercially and for you to assess the thing, would be to agree a grid problem with your operational staff. We need folks, because it's the same to do a pilot, whether it's a real problem or a pretend problem, so we prefer to focus on a real problem that you want to address. So we begin by doing that. Then we install the system. Gridhound provides a network management system, and we'll hear about that shortly, and include maybe 6 substations or so at LV or MV, or a combination, with sensors and power quality monitoring with units from ourselves and from ALTEA. And then we provide a web cloud user interface, so you can see what's happening, and real-time data that your existing distribution management system can use, and in particular if you're doing big data analytics, you can feed into that, but you can generate a lot of data. And finally, we provide a phone app for your operational staff to deal with the more real-time outage management issues. So this would be what we'd envisage as a typical minimum project, be about 6 months, involve these sort of steps, and you can read them there yourselves. So that's what we would see as a minimum pilot. So if you're interested, we'll be over there after we finish the talks, and we can talk to you about it. Thank you.
Any questions? Thank you very much. As a next speaker, I would like to invite Andrea from Aachen University.
Hello everybody, my name is Andrea Angioni. I work at RWTH at the Institute ACS from Professor Monti as research assistant. I've also participated in this project. I work particularly on the development of the low-cost PMU and on the pilot side in our campus. So again, I want to give you a quick overview of the project. Here I want to focus on the 3 key elements of our architecture. The first one are the sensors. They need to have particular requirements, so they need to be reliable but also low cost, because the idea is to install them in all the nodes of distribution grids or in a lot of nodes. And we want to use them for 2 applications, protection and measurement, so an integrated sensor for 2 applications. Then we have the measurement devices. So also they need to be robust, accurate, again low cost, because we want to store them in a lot of points. They need to provide power quality information and synchro phasors. We will use them for state estimation later. And they need to speak basically the standardized communication protocol so that they can be integrated in the rest of the architecture. All the measurements have to be collected in a cloud system, so again a low cost but reliable solution. Again, we extract data with standardized data protocol, and then we have algorithms for state estimation. This is a graphic overview of the architecture. In particular, here I want to underline the components that have been installed in our pilot site in Adressing. we had a lot of freedom on what to install. So we tried to basically implement all the architecture. We have the sensors from ALTEA, medium voltage. We have the MAC monitoring unit in low voltage. We have our PMUs, and then all the data are sent to the cloud applications of Gridhound. Here is, I want to speak a little bit about the low-cost PMU that we developed. The key components are the intelligent part, a computer and Raspberry Pi, the data acquisition board, in this case from an external vendor, a GPS module, and a GPS antenna. For the ones who doesn't know, the PMU calculates a synchro phasor. The difference with the phasors is that we have a global reference that is valid all over the world for the phase angle that is given by the GPS. So the GPS is the enabling technology. Normally these devices are installed in transmissions and the prices are too high for installation and distribution because we speak about $10,000. So our objective was to go below the threshold of $1,000. Here is an overview of how the architecture works. So every second we send a request to extract data. Then basically 4 quantities are calculated. There is for voltage and current, magnitude and phase angle, frequency and rate of change of frequency. Those are then encapsulated in 6150 messages and then sent via internet. We also implemented encryption and authentication functionalities, so we are sure the data cannot be picked by external users. We also wanted to validate scientifically our device. So once we built the prototype, we did all the metrological characterization, and we presented in the most important international conference for applied measurement of power system. And the work was really appreciated. We also received a lot of suggestions. And there are also producers of the most expensive PMU that I already said. So from Siemens, Arbiter, and we had some interesting exchange of opinions. Here I show just the test for the metrological characterization. To give you a quick idea, the performance of the PMU is quantified as total vector error. So we measure a vector, and we want that our vector is different from the actual one, no more than 1%. So total vector error should be below 1%. Here I show the total vector error, and then I split it into magnitude and phase angle error. You can see that this is the test for the magnitude, so we test all the magnitudes that the PMU can acquire in the input. In all the cases, the maximum error was 0.1%, so 10 times below the threshold. Same is true for the phase angle. Then we tested the frequency, and in this case, we saw that the total vector error was always below 0.25%. And finally, we tested with all components of harmonics until the 50th component of harmonics. And also in this case, the total vector error was about 0.1%. So in all the cases, we demonstrated that the PMU satisfied the standard. Then we go to see a little bit how we integrated the PMU in the architecture. So here I'm speaking in particular about the RWTH side. We have sensors in medium voltage and low voltage that convert the quantity in input to a quantity that is manageable by the PMU, so plus minus 1 noise. Then the PMU sends continuously their calculated values and are connected to GPS and send values via 6150 sample value protocol. The phasor data concentrator subscribes to this measurement. We continuously read them, save them in a database. After that, an application running, in this case in Python, will extract the value every second, because we publish every second. So every second we have updated data, calculate state estimation, store them in database. And finally, we have an application to show the result. So we can see in real time how the state of the grid is evolving. This is the location where we are testing, so our campus. And this is a small schematic of the test grid. So on the left, you see that we have the medium voltage transformer, where we install one PMU on the medium voltage side, and then we install in several locations in low voltage other 3 PMUs. Here is some more information on installation details. So the sensors is a sensor installed at the 10 kV medium voltage side from ALTEA. Then we have a device that allows us to that adapt the signal to the PMU and the PMU itself. In the low voltage, we have voltage and current measurements. The first one then is brought to 10 volts with a simple voltage divider. For the current, instead we use some Rogowski coils. And now I'm going to show you the results. So what are the results that we could evaluate in our pilot? First of all, we had a lot of knowledge of what is happening in our own grid. It was actually used by the electrical personnel in our grid to better monitor the system. Also, we could compare the measurement profiles from being used in different locations. For our case, not only in our campus, but we could even evaluate PMU measurement between Germany and Italy, and I can show you some results later. Also, we modeled a small online Scala tool, so again, very inexpensive and very handy to use. And also, we evaluated the same test in our real-time laboratory infrastructure. So here are some results. First, I want to concentrate on short time window. These are the measurements in medium voltage. You can see the sine waves on the upper part of voltage and down the current. And we could see that the voltage is very balanced, no harmonic. The current also, there are very few harmonic, and you can see that you start to have a certain imbalance among the phases. When you go to low voltage instead, on the upper part we have the voltage. Again, we have to see to say that it's very balanced. Maybe we start to have a small contribution of harmonics. When we go to the current instead, due to in our laboratory we have a lot of electronic instrumentation, we have a lot of content of harmonics, a lot of unbalance. Also, the neutral components start to be quite important. Now I show you instead larger time windows, similar measurement devices. This is the online interface of our online Scala. You see on the upper two plots are voltage, magnitude, and phase angle. The reason that the phase angle is a little bit messy is because the measurement is over 2 hours. And due to the fact that the frequency is not constantly 50 Hz, basically the PMU will measure phase angle rotations. And over 2 hours you will have a lot of phase angle rotation due to the fact that the frequency is actually 50.01 rather than 50, for example. The second row are the current, magnitude, and phase angle, and the third row are frequency and rate of change of frequency. Of course, you can use this to calculate online indexes. In this case, for example, I'm showing you the voltage, the phase angles, the phases ABC, maximum, minimum, medium value over a certain window of 2 hours. You can see the sequence component, 0, positive, negative sequence, the voltage and balance factor, frequency, rate of change of frequency. Here, instead, I'm making a study on the frequency. You can see that the frequency measured in real time in Italy and Germany is very similar. Also, you can see that over 3 hours, I calculated that due to the fact that the frequency is not exactly 50 Hz, over these 3 hours, clocks that are based on the system frequency will not measure correct time. In this case, we were lucky because over 3 hours, this clock will have an error of almost 1 second. But there were a period, maybe if you remember, at the beginning of the year, where due to power outages in, I think, the Balkanic area, the frequency clock had a delay of 3 minutes, 5 minutes. These are other phenomena that we observed. We observed that 3-4 times per day there are very steep voltage variations in a matter of a second. We thought that this is due to unloaded changer. We are sure that this is not an error of the PMU because we saw that the same voltage variation is measured exactly at the same time by PMU installed in different locations, in medium and low voltage. And of course, the frequency profile is the same, measured by both of the PMUs. This is another part of the Scala. So we apply state estimation, and even if we have very few nodes measured for PMUs, we could monitor all the grid of our campus. And this is updated online thanks to the state estimation of the state of the system. Here are some indexes of how our system is performing. So we expect an uncertainty that is in the order of 0.5% of the state estimation. And basically we run every second. We can keep the real time because time to read measurement is quarter of a second, time to run the estimation is very few, and then a little bit of time to write into database. Also, the consumption of the cloud machine is very few, so we can use very economic product from, for example, Google to have a very less powerful virtual machine. We try also some tests of scalability. We try, for example, to install 2 more PMUs, and we evaluated that the increase of computation is really negligible. So this system can be potentially scaled up to several tens of PMUs. Also, an interesting part in how much does it cost this pilot site, because this is an example also when you want to install in a real grid. Now, without going into details, we can see that installation of 4 PMUs and the sensor, and in this case, remember we're speaking about low voltage but also medium voltage, cost in the order of 2,800 euros. If you also sum up the installation cost due to the fact that you have personnel, technical personnel, engineers, software developers to do debugging, the total installation cost for this PMUs is almost 5,000 euros. So, to conclude a little bit, we improved a lot of knowledge thanks to our data. We want to still learn a lot from this measurement. And also we evaluated that the ADMS solution was quite effective. So we didn't really have a lot of issues installing sensors and devices. Maybe the most important, the most challenging part was the bureaucratic part, because installation medium voltage require a period of deconnecting power, so there is a lot of bureaucracy before they give you the permission to start. And next step, we want to keep on integrating the architecture of ADMS. Thank you.
Any questions regarding this presentation? Not for now. Everyone's waiting for the networking part when they can ask questions in person. Thank you. And the next speaker is Artur. Okay, agenda has been changed. Please.
So, thank you, Mr. Löwen. Just to my introduction, my name is Matthias Schilcher from the Bayernwerk Netz GmbH in Regensburg. Let me just say some words about the Bayernwerk Netz GmbH and its grid and the demands of today and the matters to the cooperation with Gridhound. First, something about the Bayernwerk Netz GmbH in general. As you can see on the map, the grid area of the Bayernwerk Netz GmbH is roughly 2/3, or let's more say 80% of the area, as you can see on the map there. It consists of high voltage, medium voltage and low voltage, and also a lighting grid, in total amounting to almost 190,000 kilometers. End consumers are about 2.3 million. And to mention as well, there is also a natural gas grid, low and high pressure, with in total almost 6,000 kilometers and about 90,000 end consumers. And all that is run by about 2,800 employees, with me being one of them. So let me just say some words about our grid. As most might already know, there are the voltage levels in our grid, starting by the synchronous grid, the European grid, with 380 and 220 kilowatts. In our case, that's not run by ourselves, but by an Ethernet transmission system operator. An origin might be the motorway, followed by transformation down to 110 kilowatts, and that's where our grid begins. There are 11 substations with transformations from 380 and 220 kilowatts down to 110 kilowatts. It's important to mention that our high voltage network it doesn't have a Peterson coil, but it's straight connected to Earth. So this whole map, as you can see there, consists of one 110 kilowatt high voltage network. It might be compared to Federal Road with about 9,000 kilometers high voltage grid, mainly mounted on poles, some 300 kilometers as cable. Again, there are transformer stations from 100 kilowatt to 20 kilowatt medium voltage. Number is 370, followed by 46,000 kilometers medium voltage grid, mainly consisting of cables. And again, transformer stations, 44,000 transformer stations, transforming down to local grid, 230, respectively 400 volts. And as you can see, 9,000 kilometers high voltage grid, 46,000 kilometers medium voltage grid, it's already sometimes more, and 100,000 kilometers low voltage grid with 44,000 transformer stations. As you can see, the numbers are increasingly high as you go down the voltage, and that's where the biggest problems begin, because as you can imagine, in the high voltage level, everything is measured and can be operated from remote, whereas in the medium voltage level, that gets increasingly difficult. There are only some points in the network that can be operated from remote. In all other cases, a grid operator has to drive there and operate the switch. And in the low voltage level, there is hardly any remote operation. And as you can see, large-scale industry is often connected in 110 kilowatts. In 20 kilowatts, there are traditionally industry, businesses, offices, and stores, whereas the low voltage, small businesses and residential buildings are connected. You have also to take in mind that the renewable sources of energy, such as wind and photovoltaic energy, are mainly connected in medium voltage and especially in low voltage. As you can see here, the numbers list how many sources of energy, of renewable energy, of decentralized sources of energy are there in the different voltage levels. As you can see, 149 in the high voltage grid is quite a number, but even more, 4,779 in medium voltage, and this very high number of almost 270,000 decentralized renewable energy sources in low voltage. As I already said, and as Mr. Flaherty said, the increasing demand of those generators leads us to increasing problems because they are measured and they can't be controlled from remote. Here, some data, as you can see, the number of renewable energy sources has increased dramatically over the last 10-15 years, beginning from 2002. And similar growth is also expected from demand side. Let's just say about electromobility and something else like that. So we expect also a rapid growth of similar decentralized demand. And that leads to a rise in voltage, especially in the medium voltage and low voltage grids. And as I mentioned, with low to little possibility to monitor and to control from remote. To get a closer sight to that problem, we created in a high PV penetrated area, Seebach, over there on the map you can see it, a grid laboratory. Only in that medium voltage grid from the substation Seebach, we measure almost everything on medium voltage level. All stations are equipped with measurements, and also some 10% of the customers are equipped, plus some low voltage consumers as well. In this grid laboratory, it takes a great advantage to develop new control strategies, plan guidelines, and field test new equipment. But as you can imagine, this is highly expensive and it's far away from being a solution for our whole grid, would far too expensive. So although this is a reference grid, we need also a solution to use our whole grid to get more information without having to pay such high prices as used in our grid laboratory. And that's why we decided to start cooperation with Gridhound to use our existing measurement infrastructure and some new measurement infrastructure to get the best possible insight of limited measurement. So Mr. Löwen, can I say something about it?
Yeah, thanks. Let me switch to my presentation. Okay. Are you already tired? Are you still listening? Now, let me tell you something about our solution of monitoring, state estimation, and services. Yeah, we already heard a lot about the challenges in the distribution grid. We heard a little bit about the project, what we're doing, and the solution. But I want to recap the current state of the grid. The DSO's responsibility is the safe, reliable, and efficient grid operation. But current solutions don't solve all the problems they have. Either the solutions don't provide the flexibility, the extendability of the software, they don't provide observability of the grid, or they need a huge number of sensors, which, as Mr. Schilcher just said, is unaffordable. So, how shall the DSOs operate the grid if they don't know what is going on? A brief recap of the history of state estimation, which is, let's say, a concept to provide observability in the power grid. As you can see, the original algorithms are already more than 60 or nearly 60 years old. They were improved over time as even the original approach, the classical approach, was too expensive for the transmission systems. But none of these solutions were good enough for the distribution grid. The challenge is the amount of measurements and the amount of computational resources needed. And with our approach, we can solve these issues. We use a methodical approach. We start with modeling and simulation of the grid. We run thousands of local simulations. And then we use sensitivity analysis for the optimal placement of measurements in the grid. What does optimal mean in this context? Basically, we try to find the points in the grid that can give us the maximum amount of information on the behavior in the grid. And only by this approach, we can minimize the total amount of measurements needed. Then we learn and evaluate. So we perform machine learning to understand the behavior of the grid, basically creating a new information theory-based model instead of an electrical formula-based grid model. And then we can receive the field measurements and do the observation and experience grid awareness for the first time. Yeah, we have seen this slide before by Professor Monti, so I will skip it. Most important, we can reduce the amount of measurements needed compared to the classical approach by up to 90%. This is already a big save in investments just for generating observability. And then the additional benefits of observability are you can maximize the utilization of the existing grid capacity, especially if you're looking into peak shaving for renewable energy generation and in the upcoming e-mobility trend, where you basically need to manage the loads and the grid to not overload the grid. So also safe grid operation is very important in order to not destroy equipment connected to the grid, increasing the efficiency and forecasting of the grid state. Overall, we expect that we can save the operators up to 45% of the costs compared to the copper-based extension. Yeah, we started in this ADMS project from a prototype to a market-ready product. The prototype looked like this. It's a very crude one, just built in a few months. And now we are at this. And I've actually prepared a live demo for you. Hopefully this will work now. So here we can see the RWTH grid. Here we see the real-time measurements getting fed into the system. And here we can see the live capacity of the grid with each node. What we also can see is, of course, what is the input for our state estimation, some training metrics, the placement of optimal placement of measurements, and of course some details on the grid nodes and names. And when I select a node here, I can see in real time what is the current state of the voltage, and you see it's actually violating the regulatory rules. This is not supposed to be in the grid. So improvements are needed. Yeah, this is our live running system. We're permanently working on improving it and continuing building new features. But going on with my presentation, I want to tell a little bit about the work that we did with Bayernwerk. We did an offline trial one here, and we looked at the Seebach grid, which is 550 nodes in 20 kilovolts medium voltage. We have some medium voltage generation units, some nodes, and 180 low voltage feeders or transformers. And we selected 10 nodes from our sensitivity analysis. Now with these 10 nodes, we did our state estimation, our training and state estimation, and then you see we have a test point selected here. And for this test point, we looked at the error. The error is basically the key value that you evaluate a state estimation with. What error can it provide, or how low can the error be that it provides? And as you can see in the lower graph, the black dots, or the squares, are the true value coming from the simulation, and the red triangles are the values coming from the state estimation. There's barely any deviation. Also in the graph above with the big spike, you can see the deviation of the relative error. It's in the range of 10 to the power of -3. So highly accurate. On average, we have an error of less than 0.02%. A maximum error of 0.26%. These are amazing results. Yeah, so the left case is the one that I just showed you. On the right side, we looked at what will happen if I use a different set of measurements. For example, if I cannot optimally place the measurements due to the cabinet being too small, the points being underground, or whatever reason. Still, we see the average error is a little bit lower than the original one, but the maximum error is bigger. But still, overall, very good results. Then, in the next stage, we have the number of measurements. Still, very good results. To compare them, of course, you see if the measurements are placed less optimally, or we have less measurements, obviously the error will increase. But all in all, we can be very happy with these results. In these cases, we had a maximum error of 0.7%, on all the nodes in the grid compared to the simulation. Yeah, so the study could show that the accuracy depends, of course, on the grid model quality. If the digital twin of the real grid is bad, then obviously the results will not be good. But this can be tuned also in the real field once it's in application. Then, of course, number of measurements, locations of measurement points, and the type of the measurement do have an impact. But in general, the approach that we're using is so flexible that we can use any type of measurement. When the temperature has an impact on the grid state, we can use that as well. If there is a strike, we can use that as well. Every data that is impacting the state of the grid can be fed into the system. Yeah, so we can provide real-time grid awareness. From that, we generate actionable information to provide in the end safe and efficient grid operation, so the voltage stays in the band that the regulatory tells it to be. And in the end, we will use smart algorithms for full automation of the power grid. Are you still simulating, or are you measuring and estimating already? Let's talk after. And now, final word from Mr. Schilcher.
Thank you, Mr. Löwen. As Mr. Löwen already showed, the results of the offline estimation, we were quite impressed of them. So we decided to continue cooperation with an even more detailed project that's just starting at the moment. Thank you.
And it seems that we came up to the last speaker today, Rainer Frank. Stage is yours.
Thank you so much. Here we are. Perfect. Okay, I'll introduce you to our business. So it's another business. We're not talking about smart grid, we are talking about smart metering and this new digitization project that's called Rollout in Germany. My headline is, what's the headline that stands behind this is who pays the party? That's the very important topic we have to declare. Okay, let me first introduce our company. We are a small company, not so beautiful as the Bayernwerk, for example. We are very small, we are only around about 50 people. We provide services to utilities, to DSO, and all these services are corresponding to metering operation business, to this administration business. But we also provide services around procurement and wide area network, for example. This communication technology that we have to use for our smart meter installations. And then also we have to provide some services that we call value-added services and smart solutions. Our partners are, as I mentioned, utilities and DSO. We have around about 270 members in Germany already collected. Most of them are utilities, and 6 of them are special partners in our projects to develop new IT infrastructure, to develop the interface between the central IT that we use in E.ON and the IT the ERP systems that are used in the utilities. These 6 partners all have different IT systems, and so we have quite different experiences in these developments. We also doing one pilots to develop this we call PLC technology. I don't know whether it's already mentioned here. PLC technology we use for communication via this electrical power grid. Yeah. Okay, that's it. It's quite easy. We install the meter itself, the gateway, and we call this intelligent meter system. Around about 90 to 80% of the customers will get only the gray box, only this meter. The other ones will get the the whole system. And so we have different services for these groups of customers to develop. One is the, I call the stupid meter itself service, based on this gray box, and the other one is based on the whole system, and we call this smart solutions. I'll introduce you to some of these examples in the next slide. Here is the rollout plan of the legislation in Germany. You can see that we have around about 16 years to make the rollout, and you can see that we are already late. We did not start in 27, we have to start, I think, in 2019, because we don't have the hardware for the secure data transmission. The gateway is not available in the market in Germany. It's not licensed, and also the processes are not already developed, and so we have problems to provide this technology to our partners. So we will start in 2019, and then we can reach 3 years later the 10% target for the installation of the smart meter, this intelligent metering system, and around about 10 years later, we'll reach 13 years later, we'll reach a 95% minimum value that is the government says us that we have to reach in the whole grid, because around about 5% is not it's too expensive to install the meters. Yeah. Okay. Here you can see also the groups of customers that we have to install the meters, and you can see these are the smallest customers are the group from 6 to 10,000 kWh. We have to install a meter, and we will get a price, we will get a regulated revenue around about 100 euros. That's the revenue, and now you can see the customer value, and I would say there's nothing new compared to the old meter. There's nothing new. We provide the billing, we collect the data, we manage the data, but there is no new revenue, no new value for the customer. So the customer only has to accept a higher price, and that's a problem for us in Germany. And therefore, we expect cherry picking of the competitor metering operator. He will took the groups of customers where we can get a higher value for this price, and then he will prevent also any energy delivery product or any value-added services. And this bundle he will call a smart solution, for example, and we will lose this customer. That's the expected development in German market. So we have to look on the business case, and where can we get this better economical calculation. Here, let me back. Okay, here. Let me introduce you to the slide. The red bars are the costs. Here you can see the main costs are the mounting itself and the meter operation, the devices, and the van operation. These three topics are around about 60% of the costs. The rest is the administration, the initial project IT, the doing that has to be done in the meter operator, respectively in the PSO, and is only around about 40%. So you can also see here is this blue line, and the blue line shows the revenue that we can get from the customer. It follows directly to the figure of rolled-out meters, and it depends on the meters, on the BOG, on this limited revenue, and also on the sold value-added services. If we have here more value-added services, then we can shift this blue line to higher values, and also the black figure will rise, and this break-even point will come to earlier point. Sorry. Okay. So we have to provide value-added services. That's the idea. Now I have to use the some value-added services. Excuse me, Martin. Okay, perfect. That what we call the smart meter value pool. All of these are ideas around this intelligent metering system and around the meter itself. Now I can show you, for example, a product that we already developed for the meter. The stupid meter, we call this the prepaid next generation product. It's based only on the meter, and we have something like you can use any smartphone to load your energy via Bluetooth to the meter, and the meter would count the value, and then after and then after when you reach a defined value, you get an alert, and then you will break the energy, and then that's really called prepaid energy prepayment, and it can be used, for example, in charging stations, not only for cost control in social critical households, but also in charging stations, for example, in marinas, in camping, in any apartments, for holidays and so on, and everywhere in these places you can use the prepayment solution on the meter. That's the present product that we have, or that we already have. Sorry. Now I can go to multi-utility. It's the meter, and we can here you can see this WAN, this wide area network data connection. Here you can see the other meters, and here you can see different media. And the first step we will use the gas meter to bind together with the gateway, and then we can use the WAN gateway connection, not only for the electrical power, but also for gas, for example, but also some application for heat, for example, is thinkable. Sub-metering for heat, for example, is very interesting, and we are also developing these products based on this technology. And now let me have a look on this control. This control is a wide range of applications available. The control unit is sitting here beneath the gateway. Here is the control unit, and we can control, for example, white goods or renewables. We switch renewables on and off, for example. We can control e-mobility stations with loading, for example, storage, respectively. Gas metering will be available, and even heating will be switchable, and even smart home products can be connected to our meter, and therefore we have something like a platform for any smart solution using this technology. Yeah, that's it. I think we have 50 minutes. Thank you.
Thank you very much. Any questions?
I'd like to know if you plan to perform a periodic verification of the meteorological characteristics, accuracy of the meters.
In precipitation.
If you plan to do that.
If we have a big data model for this, then we will plan it, but it's not a present situation. No.
In Romania, I know we have 10 years period from Romanian Bureau of Meteorology that all the meters, no matter it's ground or whatever, has to be checked.
For the smart heating model, for example, we plan this, but it's not already implemented. Yeah.
Any more questions? No. Then thank you very much. So it seems that we actually reached the end, or finished the official part. Before I let you all go and talk to each other and ask all of the questions that you did not trust yourself to ask here, we'll do a little agile kind of goodbye. So we used to, in a lot of our events, and I guess I see some faces that I've seen before. Do you know what is emotional checkout? No. I see some people laughing. So I will give the microphone to a few random people, and you need to say, what is your emotional hashtag for today? After this event, how do you feel? As I know some of the names, if there are no volunteers, I'll pick on them. So my emotional hashtag for today would be learned a lot and but tired. So I'm very happy that you are all here. I absolutely enjoyed this event. I hope I speak in the name of a lot of us that it was interesting. It was nice to see this whole combination of different people coming from everywhere in different areas and sharing the experience. Karen.
My hashtag would be inspired.